Hello and welcome back. It's been a while. Ever since SDXL 1.0 came out, I was curious about how it stacked up against SD 1.5, so I started conducting many tests with SDXL, including fine-tuning models, training LoRa's with free learning rate optimizers such as D-Adaptation and Prodigy, setting up node graphs in ComfyUI, and exploring additional compute power on Runpod. So if any of these topics sound interesting to you, let's get started. I'm going to start off by showing this node workflow graph in ComfyUI. My installation is directly cloned from GitHub, so I'm not using the recommended executable file found on the releases page here. The base graphs were provided by Comfy Anonymous themselves at this link, so there's two. This one is the normal one, and this one you can have a custom refiner. Download the image files, then you can load them in ComfyUI as a workflow. Just to clarify what I mean, right-click on this image, click Save As. Save it wherever you want. I'll just save it here. And then go back to your ComfyUI. You can go to here, on the right, Load. And I think I saved it over here, ComfyUI image, and then you can click on this image and then open it. I'm not going to open it because I want to preserve what I have here. Anyway, on the right side of my UI, I've amassed groups here in the hopes of showing comparisons between SD 1.5 and SDXL. You can see the SDXL base model in yellow, the Finetune models in blue, the SDXL LoRa's in green, and finally the SD 1.5 groups in purple. This first yellow panel on the left shows the base SDXL 1.0 model. You can already see that the image here is pretty decent. It feels kind of painterly and seems to follow the prompt well enough, which is this over here. Very standard, wearing Alexander McQueen fashion, white hair. And it's a good starting point to analyze the effect of our trained models, because you can see how well these other models are following this prompt. For the dataset, there were around 408 images with a 1024 by 1024 square pixel resolution. Some of the images are from previous Dreambooth models or LoRa's. And for the captions, I prepended a tag of kasukanra STY as the first token. This is important because you'll need it to activate the LoRa at least. In ComfyUI, you recreate the flow of diffusion models, which follows loading the model, using that model's CLIPTextEncoder along with your input text down here, to influence our latent noise, which I initialized somewhere over here. And then you connect this to your sampler here. Clip is simply the method to convert text into a vector so that the neural network can process what's going on. Since I showed my dataset and I showed that I was using a trigger word, I've split up the trigger word and the rest of my prompt using the custom nodes from the WAS node suite. I asked around in my Discord channel about this functionality and the user dog showed me it. So here we are. Thank you, dog. Here you can see that I have two different texts for the positive prompt. So I have this normal text here with my trigger word, and then I have the raw rest of the prompt, and then I concatenate it. The reason why I do this is because when I put in the raw prompt here, this only goes into the base model because remember, the base model is not tuned, so it doesn't notice what a trigger word is. And for the rest of the models, I do use the dataset that I trained on, which does have this trigger word of kasukanra STY. This makes it that much cleaner because I don't have to copy and paste this prompt over and over again, which would become very, very tedious. Like that. I can just change it here, and then it'll be changed for the base model and all the fine-tuned models and LoRa models. So if we jump to our K-sampler node, any of them will do, like this one, You can see that they all connect to a refiner node in the end. Nothing fancy here. One thing I want to point out though is that I'm using CLIPTextEncodeSDXL node. So here, you can see that I've basically repeated both of the prompts for text G and text L, and I'm using the same prompt for both of these. So text G and text L are identical. There is a short report I found written by Bluefo here on Google Docs, and he basically came up with the conclusion that you should use the full prompt for both clip G and clip L. So this is the TLDR. Lastly, just to show how to create this CLIPTextEncodeSDXL node, double-click anywhere on the empty graph, and that brings up your search bar. Type in CLIPTextEncodeSDXL, and it's right here. Bring it up, and you might wonder, how come yours doesn't look like mine? Or how come these two are not matching? Well, basically, I converted these clip G and clip L into inputs instead of using a widget. To do that, just click on the node, right click, and you can see the list here. Convert text G to input, and then also convert L to input. So there you have it, and you can just keep reusing this for your negative prompt as well. So you can see my negative prompt here is also using double G and L. Now that we have a general idea of what the images look like, I'll go over how I chose which epoch of each individual Finetune model to use. In the past, I used the XYZ plot script in the automatic 1111 web UI to generate these kinds of comparisons. Let's start from the basics with the Finetune models. Before showing how to replicate the plot script in ComfyUI, I'll go over the fine-tuning training process and the design choices I made for context. First up is the naive approach with Adafactor, or adaptive learning rates with sublinear memory cost. So this result here. Speaking from personal experience, Adafactor has never performed well for me in diffusion model training as well as my own professional machine learning work. So I was already pretty hesitant on using the Adafactor. Initially, I looked at this Guides tab on the Koya SS GUI repository by bmalte. So if you click on the Guides tab right here, you can see the recommended settings. So I took a look at it. It says use Adafactor and these optimizer arguments, and then constant with warmup, etc., etc. So I said, sure, why not? I need to get a baseline output anyway. Unfortunately, unlike several of the people who have been active in SDXL's development or invited to participate in it, I didn't have any prior knowledge to go off of. As such, when I started fine-tuning locally, I was pretty disappointed to find that SDXL 1.0 could not fit into an RTX 4090 during training using the Adam optimizer. If you look at the comment here by K-Mac McFarlane on the bmalte GUI repository issues, he's using settings that are pretty similar to mine, and I was not able to figure it out, and neither was he. Eventually, I was able to fit the training into an RTX 4090 using the settings provided by Carolina Banana, and I'll show those here. Don't worry about copying down all these settings or pausing the video or whatever, because I will be sharing all of the settings I used for all Finetunes and LoRa's. So this is just for the high-level overview. If you look over here on the very beginning, first tab, Source Model, make sure you click SDXL model, and then you can go over to folders and set up all these folders here appropriately. One thing that is different is that you need to create a training config folder as well. The reason doing so is in your dataset preparation, Koya trains from something called metadata that it creates. So it will generate these two metadata files, meta_cap and meta_lat. Make sure you are generating these like so. Otherwise, your training will not work. Then we can go over to parameters, which is the bulk of the training settings. I went for 20 epochs. My trained batch size was 1. Anything higher than a trained batch size of 1 would run out of VRAM on my machine, which is using an RTX 4090. Other than that, I'm going with BF16 for my mixed and save precision. And then I enabled cache latents and cache latents to disk, which you almost certainly have to do if you're training locally with a consumer card. And if you enable these two options, you cannot enable color augmentation because they clash. After that, you have to change your optimizer to Adafactor, and you can set your warm-up steps if you want. You set your scheduler here, constant with warmup, but this actually doesn't matter because it'll automatically switch to its own Adafactor scheduler. And I went low on my learning rate compared to what it recommends. It says 4 times 10 to the negative 7. I chose to train even more slowly by 2 times 10 to the negative 7. Other than that, you have to add these optimizer extra arguments, scale parameter, relative step, and warmup init. So I didn't take too much time to look into what these parameters did because I was already kind of convinced that Adafactor would do poorly. You can, of course, look into this if you are an Adafactor believer, but I am not. After that, there's SDXL specific parameters. Make sure to check this, no half VAE, and also make sure to check cache text encoder outputs. If you do not check this, you cannot fit your training into a 24 gigabyte VRAM card. Okay, and this will probably be checked, I'm not sure. Make sure to uncheck the train text encoder. The reasoning for this is that SDXL has 2 clip encoders. In order to avoid collisions or clashing or confusion, let's just don't train the text encoder at all. Okay, and then one more thing I want to point out is that there's additional parameters down here. I added this max grad norm 0.0 in. When I ran it normally without this, the script told me you should be using max grad norm equals 0. So I was thinking to myself, okay, I'll just do that. I'm not sure if it makes a difference, but it's a recommended setting. And since you're using cache text encoder outputs, you can't shuffle your captions, which already makes me feel like Adafactor is also ruining everything for everyone. Next up is noise offset here, which I've set to 0.0357. The reason why you want to introduce some noise offset, or why I like to introduce some noise offset, is because the normal latent space gives you very flat images. If you increase the noise offset, you can get more contrasty or more vivid, more dreamy, more etc., more randomness in your generations. In the past, I would always be using a value of 0.1. However, when I put this into this training script, it told me that 0.1 is too high. SDXL was trained on a noise offset of 0.0357. So I just copy and pasted that warning into this training setting file here. Lastly is min SNR Gamma, which initially is at 0. I've turned it up to 5. If you want to go in depth, we can take a quick look at the min SNR Gamma paper here on archive. And on the initial page, the very first page right here, it says that the min SNR Gamma training converges more quickly than the baseline training by a factor of 3.4, which is quite fast. But if we're trying to speed up training, then we don't really need to use this, right? However, if we go more in depth on the proposed method here, they list 3 claims saying that by using min SNR Gamma, you can avoid setting loss weights to 0 for sparsity, and then you can decrease the noisiness for each gradient for each iteration in stability. And lastly, you can speed up training inefficiency. So all this math stuff, you can take a look at it if you're interested in it. However, what really grabbed my attention about this paper is when they showed the graphs here. These plots show that when you're using the min SNR 5 here, you are actually getting very decent results on a longer training. So with that being said, I felt, why not use 5 as well? So there we go. Now that we have a good overview of the training settings used in local Adafactor optimization fine-tuning training, what a mouthful, we can open up the Tensorboard to take a look at how the training progressed. Normally when you're training, you can open up a start Tensorboard at the same time. However, once you're done training, you have to open up a Tensorboard log on your own. So if you want to install your own Tensorboard library, first of all, make a directory, just call it Tensorboard temp, and it's created, cd into that. Now you want to create a virtual environment, I'll just call mine VNV. Okay, now that that's done, you should have this VNV directory here. You can activate it, VNV scripts, then activate like that. It's created. Lastly, all we have to do is install Tensorboard. Like that. Tensorboard is done installing. So to run your Tensorboard, all you have to do is type in Tensorboard, then -- log dir, and then paste wherever your log directory is. Mine is here. So let's go ahead and do that. And yes, it says that my Tensorboard is running at localhost 6006, so let's head over there. If you go to your localhost 6006, this is what shows up. And what we really want to look at is this loss per epoch. It should be going down, and it is. This is a very classic graph. Nothing to see here. And you can see that my alerting rate is at 2 times 10 to the negative 7. As I said, it goes up, it warms up this amount of steps, and then it's flat all the way like that. You can see that my epoch is at 10. I originally trained it for 20 epochs, but at around 10 epochs, which was already 24 hours, I thought to myself, I'm not going to invest any more time in this failed experiment, so let's just cut it here. Now that we have a little bit more context on how fine-tuning with Adafactor worked, we can jump back into ComfyUI and evaluate the results once again. So you can see that there isn't that much of a change, if at all. This is the base, this is Adafactor on local fine-tuning. This is pretty conclusive with our results, because if we jump back into Tensorboard and take a look at this loss per epoch, we started around 0.1004 as our initial loss, and we only made it to, let's just say, 0.098. It was barely 0.0006, 0.007 of a difference in loss, which you could say is pretty negligible. So I don't think that fine-tuning locally with Adafactor for 10 epochs with a batch size of 1 is doing anything. So I very quickly thought I need some more powerful hardware to train with and to change the optimizer. Once I realized that fine-tuning locally was never going to work feasibly due to the training times and poor results, I looked for cloud GPU training options. Runpod was introduced to me by another user in my Discord channel named Raf. Thanks, Raf. So I got to work opening a Runpod using a powerful GPU on the secure cloud. In my case, I opted for a A100 GPU with 80 gigabytes of VRAM, so it's this option. And I'll go ahead and show my pod here. It's this one. In my case, I set up the Runpod with a default template of this one, PyTorch 2.0.1. Before I connect to my pod, I want to show you the extra options that you can do. So if you click on these 3 bars on the left here, it says more actions. Click on it, you can edit your pod. And you can see that I'm using this template here, as I mentioned before. It's in a Docker image name. And if you need to add more volume to your disk, I needed around 150 gigabytes because I'm working with fine-tuned models. Each epoch will output around a 6 to 7 gigabyte file, and 20 epochs. You do the math. Okay, so let's just connect. And you can connect using an SSH terminal if you want. If you're just a casual, you can use this Jupyter Lab. So let's go with that. So we're in now. There's a workspace folder, and make sure all your files are in here. If they're not, they'll be deleted when you stop your pod, if they're in another location. So you can see here that I installed both the bmulti GUI and the Koya SD scripts. So this is the scripts, and this is the GUI. If you want to start the GUI, just cd to Koya, and there's instructions on bmulti's GitHub repository, and I've already gone through all of it. To start the GUI, just paste this in GUI.sh, and it'll start up a Gradio server, and it'll give you a specific link to go to. So it's done booting up. Right now, there's no GPU connected, so that's why it's saying using CPU only torch. So let's just copy that over, or we can click it, and it opens up the GUI that we all know and love. So here we are. This should look pretty familiar. And one thing before I go over the settings for my second fine-tune test is I want to show you all how much money it costs to train everything. So right now I have around $13, $14 left on my Runpod, and I spent this amount of money. So it comes up to be around 210 US dollars. This is to train all the fine-tune models and also to train all the LoRA models. Your mileage may vary, but I had to conduct a lot of tests to find out the ideal settings that work for me. So hopefully I save you all a couple hundred USD if the settings that I use work for you as well. I'm back in the local GUI, and I'm going to open up the JSON settings that I used for my second fine-tuning on the cloud, which are here. Final training settings, and fine tune, and open these up. So you can see quite a bit has changed here. First, you can see that I've changed from Adafactor to Adam 8-bit for the optimizer. I've also changed to cosine with restarts for the learning rate scheduler with a 10% warmup here, and a learning rate of 1 times 10 to the negative 5. I've removed all the extraneous Adafactor arguments from the optimizer extra arguments. Also, I've removed cache text encoder outputs because I need to be able to shuffle captions. It's very important to do so, but make sure you keep your end tokens to 2. The way I've set up my dataset is my very first token is my trigger word, and after that is a general global term for that picture. Everything else is the same, but make sure to remember to keep train text encoder unchecked because there's 2 text encoders or 2 clips, and we don't want to train those at all. However, I did enable one unique function which is only available in the GUI repository and not the SD scripts, which is the weights and biases logging functionality down here. So in the advanced settings, you activate it by clicking this check mark, and then it's enabled. You'll also have to add a weights and biases API key. This is mine. By the time you're watching this video, this will be deleted, so you can't use it. Sorry. To get your API key, you can make a free account on the weights and biases AI site. And then once you've gone there, you can go to user settings, and then your API key here is in the danger zone. Now, you might ask, how did I come to the learning rate of 1 times 10 to the negative 5? Initially, remember, we used Adafactor, which said it was trained at around 2 or 4 times 10 to the negative 7. However, we can up the learning rate really high, maybe 2 magnitudes above, and then set a longer warm-up step, which is what I did. I set a warm-up of 10%, and I started high at 1 times 10 to the negative 5, which is 2 magnitudes larger than 4 times 10 to the negative 7. To make sure that I could hone in on this 1 times 10 to the negative 5 starting learning rate, I basically shotgun many attempts. You can see all of them on the left side. And I ran it for 1 to 2 epochs to see what the initial images looked like. So if we look at Fancy Feather 22, Glad Dust 17, and Treasured Plasma 23, they're all very deformed images. So we can look at the highest one. If you look at this blue vector over here, it's Glad Dust 17, and I was trying to make it go to around something in the something times 10 to the negative 4 value. So about 3 magnitudes higher than what stability used to train SDXL. And then we can look at the other ones, Treasured Plasma 23. So it's this green one. This one is lower. And then I went lower and lower, progressively lower and lower until I landed on this one, which is Autumn Pond 25. So this result here. And if we click on this individual trial, we can see how it worked. So first I would do the warm up all the way to 1 times 10 to the negative 5, and then slowly decay all the way down. This is reminiscent of a cosine learning rate scheduler. However, if I'm using cosine with restarts, it should be resetting every epoch, which it's not doing here. So I'm not sure if it's a bug or not, but that's just how it was for me. However, I was still able to get very satisfactory results. And what really helped me was outputting these sample images in the sample.txt file. So let's just go back here again to Koya. And down here you have a sample images config. Here you can put in your prompt. This is the prompt I chose to use. I kept the seed the same, and I outputted every half epoch. So 340 steps was a half an epoch for me because I was using a batch size of 6 and an epoch of 25. Here I am in my image browser called XNViewMP. It was recommended by developers or contributors to ComfyUI, as you can use it to look at metadata if your image was generated using a diffusion model. Right now I don't have any metadata here because this was generated through the GUI, and I guess it has its own kind of functionality and image labeling, so it's not available here. Anyway, we can click on this and see this is the very first step, so 340 steps, 680, so on and so forth. And it keeps going and going, and I'm just letting it run. Eventually it will converge on a certain image, so here it starts converging and it's just churning now. And when it's churning, you can just let it write it out all the way to the end, because you're not getting anything more drastic because your learning rate is decaying. And eventually this is the end, and it basically more or less fits the aesthetic that I had in my data set, so this is what I used. However, if you aren't convinced by these sample images, you can do a batch processing similar to the XY plot that I showed in my training LoRA videos as a sanity check. To do a XY plot in ComfyUI, you'll need the efficiency nodes by Luciano Chirino. You can install it from the ComfyUI dependency manager in the bottom corner here. So if you click on this, you can click on install custom nodes, and it'll take a little bit of a while to load up. If you search efficiency, you can see that I already have that installed as well. I'll also be providing all of my ComfyUI workflows, so you don't have to worry about screenshotting this or whatever. Once you have the nodes installed, the way I set up the XY plot is by first using the efficient loader, which is right here. Remember, if you want to look for it, double click on the empty graph, just type in efficient, and then there's an efficient loader right here. You'll need this mainly for the reason that there's a dependencies output node from here in green that goes into an XY plot node here. And just, there you go, XY plot. This XY plot script goes into the efficiency nodes for the K sampler right here. Same idea. To find it, just type in K sampler, and then there it is. You don't have to use the conditioning from the efficient loader. You can see that I'm not connecting this to positive and this to negative. Instead, I'm using the default loader over here and encapsulating the CLIPTextEncodeSDXL on my own custom node setup using WAS suite that I mentioned earlier in this video. You'll need to specify the location of your fine-tuned models on your machine, like so. I've already copied them over from the server to my local device. When retrieving your files from the Runpod, I recommend you to not use the Runpod CTL, which is a script or some scripts that Runpod provides to you to transfer files to your machine, as it often gives the EOF or end of file error for especially large files. What ended up working for me is open a pod, make sure it's running, and then instead of connecting, click on this button here to do Cloud Sync. I use Cloud Sync to sync to my Dropbox. You'll need to set this up accordingly depending on which cloud storage provider you have, and I'll post that link in the description as well. To tell the plot which models to use, let's go back here. You'll have to open up a manual XY entry. So double click, type in manual XY entry, info right here, and then you'll see all the information about the models in your models folder and all the LoRa's, whatever. You can see that the very first few ones here are my fine-tuned SDXL models. So I just copy that. They're all separated by a semicolon already, and then I'll paste it in here. But instead, I'll just create a new one so you guys can see what it's like. Manual XY entry, XY input. Since I'm using a checkpoint and I want this to be graphed incrementally and along the x-axis, so I want it to be horizontal and not vertical, let's put x type to checkpoint and then paste all that information that I got from this entry info node. Just connect these up, x to x, y to y, and then generate. I've already generated with qprompt, so I'm going to open this up to show you. This is the same image browser from before that I showed you all. Let's zoom in with Control and middle mouse scroll up, and then right click and drag to move around or to pan. So we can see here, this is the first epoch, second, third, fourth, so on and so forth. And you can see that it's starting to converge, if not yet, but soon. Here we go, around epoch 14, it starts to converge. You can see that the image is not changing too much. At this point, remember, if we look back at the graph, the learning rate is decreasing a lot, which means that it's learning very little, but it's still learning. So this would be part of the churning phase. And even though it's churning, it's not overfitting. The last epoch still feels fine to me, and that is the epoch that I used to show you at the beginning. Now that we've established a baseline of what fine-tuned models can do, we can start training some standard LoRa's. Remember, the point of fine-tuning a model with the dataset is to see what that style model should output as a baseline. Our trained LoRa's should give us this same kind of sketchy, painterly, semi-realistic style. So let's start with the deep dive of SDXL 1.0 D-Adaptation LoRA. By the way, if you're wondering why I didn't fine-tune using a learning rate free learning optimizer such as D-Adaptation or Prodigy, these methods ran out of VRAM memory on an 80GB A100 GPU, which is quite unfortunate. In addition, fine-tuning takes around 30GB of VRAM, which is around how much D-Adaptation and Prodigy take with gradient checkpointing enabled. Anyway, this is the D-Adaptation image, as you may recall from the comparison workflow. Now, let's jump into the settings that I used. They're a bit different, but much of the advanced parameters remain the same. First off, we're in the LoRa tab, as opposed to the fine-tuning tab in the previous test. Here I've set the LoRa type to standard down here. Also, for the optimizer, I've set it to D-Adapt Adam, which is basically the Adam optimizer but with the self-learning rate layer built on top of it. I changed the warmup percentage to 5% and the learning rate scheduler to cosine. For the learning rate, I've changed it to 1 here, as well as down here in the text encoder learning rate and UNet learning rate. In the past, you would have different values for both of these, but now in the recent 3.0 update mentioned by Koya himself in this GitHub issue, so this one is in Japanese, but if you go down here, he says that you have to have 1 learning rate for everything now. And this is straight from Facebook research, D-Adaptation. So just make it 1. Next up are these optimizer extra arguments of decouple, weight decay, betas, and growth rate. To understand what's going on here, let's head over to the D-Adaptation code on Facebook's GitHub repository. This is the repository page for D-Adaptation, but I've also cloned it locally. Since I mentioned that I was using D-Adapt Adam, here I am in this Python file. Let's go in order starting with decouple. Basically, decouple means performing the weight decay separately. Here I've set up some Vim bookmarks so we can jump to the salient areas. So let's start here, line 154. If decay is not 0 and not decoupled, meaning decouple is false, weight decay is applied to the gradient update step after backpropagation. This is what is normally done or was done before in the past. So here you can see alpha equals decay. However, if decouple is true, you jump to line 235, so this one right here, and you can see that instead of decay in the alpha, you have decay multiplied with DLR, which is the current D-adaptation learning rate. So let's jump to where DLR is declared here in line 125. D multiplied by learning rate multiplied by bias correction. D simply stands for what the current D-adaptation estimate is. So the question now becomes, why is this decouple option so important? Well, if we head over to this paper here on archive, let me just open it up. Decoupled weight decay regularization. It was published in 2017 and revised in 2019. In this paper, it basically states that direct coupling leads to poor results, such as lower optimization stability and worse generalization, which are these first 2 points, especially in adaptive optimizations such as Adam, which is what we're using. Something of interest here is that Adam generalizes 15% better right here with regards to test error. This is a pretty significant improvement. Lastly, if you've ever wondered what the AdamW 8-bit stood for in the optimizer's settings, Adam with decoupled weight decay is represented by AdamW. Please recall that AdamW 8-bit is what I used to fine-tune SDXL 1.0 with pretty good results. So it really does come full circle. Now that we understand what decouple does, it directly ties into our next argument, which is weight decay. I set it as a 0.2 value. There isn't too much going on here, but there is a simple rule you can follow. So let's head over to the code, go to the weight decay, and it says an L2 penalty right here. When you have a low weight decay, you can lead to overfitting. This makes sense because you're not escaping the dataset that hard, so your results could potentially be very similar to the dataset. Conversely, if you have a high weight decay, you can lead to underfitting and just spewing random generalizations in your outputs. This is kind of a tough hyperparameter to optimize around, and I definitely think that I didn't raise my weight decay high enough for D-adaptation. My reasoning is if you head over to the comparisons that I did, you can see that Finetune and Prodigy LoRA are pretty similar. You could say they're interchangeable almost, but you can see that D-adaptation is still very semi-realistic, I would say. And this D-adaptation LoRA for SDXL and D-adaptation LoRA for SD 1.5 are very closely related because I used quite similar settings for both of them. So I would say that probably either my weight decay is wrong or my growth rate is wrong, which is this one. Next up is betas and growth rate. First, let's look at the code to see what that entails. Here in line 56, you can see the betas are initialized in a tuple with a default value of 0.9 and 0.999. The first value is beta 1 and the second value is beta 2. For the default beta 1 value, we can just leave it as 0.9. It fulfills the boilerplate running average of the gradient for the standard Adam optimizer. Anyway, the beta 1 and beta 2 arguments are equally significant in some parts of the code, with beta 2 taking on a more prominent role later on. So let's go to the first occurrence, which is on line 120 right here. If you're using bias correction, then beta 2 and beta 1 play a role here. However, if we go back and look at bias correction, on default, it's off. So I'm also not enabling it, so we don't have to worry about that. Just leave it at 1. Next, if we go to the second significant part, it's on line 178 and 179. This is the part where the root mean square propagation, or more commonly known as RMS prop portion of the Adam optimizer, is updating the exponential moving average. However, at this point, it diverges on line 186 and line 207. So if we go to line 186, you can see that beta 2 is playing a role by itself in calculating the numerator underscore weighted value. And this value is later used down here in line 207 to calculate d hat. If you didn't know, the function of D-Adaptation is to automatically adjust the learning rate for each step. So with the computed numerator underscore weighted value, you can calculate the d hat here, which is the estimated amount of adjustment needed for the learning rate at each step. Once you have the d hat, you can update the d value on line 208 provided that you don't exceed the growth rate, which is another variable we can initialize in the extra optimizer arguments. So that was the theory and implementation behind betas and growth rate. But how do we actually select usable hyperparameters for these? Fortunately for us, a user named Dr. Head showed his experiments on a GitHub issue on the D-Adaptation GitHub repository issue page. So in this issue, support for LoRA, LoRA, I don't know, I think it's part of Licorice or not, I'm not sure. You can see here that he's saying that he's using a growth rate of 1.06, and this gave him the best results. I was a little more conservative, so I used a value of 1.02. I wasn't sure how far I could push it at this point. If I were to repeat the D-adaptation training process once more, I would be more aggressive with the parameters by increasing the weight decay and growth rate. As for the betas, he also gives a anecdotal experimental story here. He says that you get better results if you use 0.99, 0.98, or even going as low as 0.901 for beta 2. So I trust what he's saying because I also had these similar results. The next thing I want to go over is the dimension selection. So here in the GUI, we scroll down and we look here. Network rank dimension 256, and for alpha, I use the same value as well. There is plenty of anecdotal advice about setting the alpha to 1 or half of the network dimensions, and people just accept that as the gospel truth. However, Dr. Head also mentioned this issue in this post. His conclusion is that D-adaptation behaves inversely proportional. Right here, the smaller the dimension size, the faster that the model will train. And this value also depends on the beta 2 value. In the past, I was already keeping the dimensions high and alpha dimensions equal to network dimensions because I too observed a similar phenomenon. However, it's good to know that other people have come to a similar conclusion. Keeping the network rank and network alpha high and equal to each other is the way to go on this kind of D-adaptation or Prodigy training. With that, we should be able to wrap up the settings overview for D-adaptation. Remember to keep the extra network parameter to train the unit only here in additional or advanced configuration here, because SDXL has 2 text encoders and we don't want to train any of those to avoid collisions or clashing. For D-Adaptation, I trained this on the Runpod server using Koya's SD scripts. As it was not trained with the GUI but instead from the command line, I don't have a weights and biases log for this specific run. So let's go old school with the Tensorboard again. This time I have the D-Adaptation loss graph open. You can see here on the right for loss per epoch that the loss is going down very slowly. After 22 or 23 epochs, it's only descended down to 0.09 from around 0.1. Also, if you check the average loss on the left here, it's still decreasing, which means it hasn't even reached the churning phase yet. So this is the very first epoch, and we can keep going second, third, fourth, so on and so forth. Eventually, it gets trapped around here at this realistic looking image, which is not at all representative of the dataset. So we can consider this a failed training. However, this is very useful information. It's important to understand where the mistakes came from so we can improve it for the next training, which is training LoRA with Prodigy Optimizer. I'm back on the comparison workflow in ComfyUI. I've also loaded in some more extra outputs on the right here from the Prodigy LoRA model, just to show how closely it matches with the Finetune model's output. So this is fine-tuned, Prodigy, Prodigy, and Prodigy. So here is the D-Adaptation repository page I showed earlier. Down here, there is a section called New Prodigy. Here, the statement is saying that Prodigy grows the adapted learning rate faster when compared to D-Adaptation in theory and practice. Please try it out if D-Adaptation is underestimating the learning rate. Well, isn't that a coincidence? Our LoRA model trained with D-Adaptation was quite underfitted, so Prodigy sounds like something we could definitely use. Once again, let's get into the training settings to better understand why Prodigy matches up so well with the Finetune model. Since we're reusing much of the D-Adaptation settings, we keep the batch size at 6 and the epochs at 25. I changed the optimizer here to Prodigy from D-Adaptation, and the LR scheduler to cosine annealing. What's here? It says cosine with restarts, but that doesn't matter. It's actually using cosine annealing down here, which I changed in the additional parameters. These settings are recommended by the creators on the repository, so let's go there. Prodigy, go down here. We recommend using cosine annealing with the method here, and then there's another sub hyperparameter called t_max, and this should be equal to the number of epochs you have. So let's jump back here. I have 25 epochs, remember, so my Tmax is 25 down here, and cosine annealing LR. More importantly, let's go back here to the optimizer extra arguments. If you recall, I used 0.2 here for D-Adaptation. Since I had an underfitted result, I thought that I should be more aggressive with the weight decay, so I upped it to 0.35. In addition, I enabled use bias correction this time, whereas I didn't enable it on D-Adaptation. I wanted to clarify something here regarding the optimizer extra arguments. If you're perceptive, you will notice that I didn't include decouple equals true here, like you should. The reason for that is that I loaded in an older Prodigy training settings JSON file and didn't notice while I was recording this part. Anyway, let me open up the final settings that I used, which are here. The main differences are that I first enabled AdamW style weight decay here, so decouple equals true. Then I increased the weight decay even further to 0.45. Lastly, I changed the epochs to 30. So before it was 25 here, so I changed that to 30. So if you change your epochs to 30, you also have to change your Tmax down here. Don't forget, so it's here 30 as well. Lastly, I have this safeguard warmup equals true. You don't really need it because I have 0% here. I don't know why I had it here, but if you don't have any warmup, this is optional. As for betas, I decided not to do anything here because I felt that the results I was getting were decent, so I didn't explore that option in Prodigy. Let's just jump into the code for Prodigy just to refresh ourselves on what use bias correction actually does. You can see here in this Python file that it says class Prodigy, so we're in the right place. If we jump to line 123, if use bias correction is true, then you will affect the adaptive learning rate in line 128 here. See, you're multiplying D by learning rate by the bias correction. My reasoning was that I wanted a better guarantee of early stage convergence by enabling this bias correction. While we're at it, let's look at D coefficient. If we go back to the training settings, you can see in optimizer extra arguments, I set D coefficient equal to 2. If you look at the code, this basically controls how large D hat becomes. See here in line 212. The larger the D coefficient is, the more aggressive of an update you can have in the learning rate. Practically speaking, you can think of D coefficient as a kind of learning rate multiplier. It makes the optimizer more sensitive to gradient updates. Lastly, I want to explain my reasoning for not having any warmup right here. You can see that LR warmup is 0%. On the repository, it says to avoid issues with linear warmup, you should use safeguard warmup equals true. They have this warning beforehand that says the method might see slow progress and overestimate the learning rate. So I thought to myself, I'm just going to bypass the potential problems and issues by not including any warmup. So hence 0% here. Modern problems require modern solutions. Once again, we should look at the logs to understand what happened in the training. Luckily, I trained on Runpod using the GUI this time, so we have the weights and biases for the Prodigy Optimizer LoRA training here. You can see there's 2 runs here, so let's go with the first one, this Ethereal Cosmos one. If you look at the average loss per steps, you can see that we started from 0.1, and after about 20,000 steps, maybe 18,000 steps, we got down to around 0.06, which is quite a significant difference. So if we also go back and look at the second run, this run was conducted using the final weights from the first Prodigy training, and those became the initial weights here. The loss decreased even more down to around 0.035, but I found out that it overfitted, so I didn't end up using any models from the second training session. Also, if we just go back to runs again, you can see that the ending weight here became the initial weight here. The claim that the authors of Prodigy made saying that it would train more quickly compared to that of D-Adaptation is pretty well founded based on my sample outputs. Just for good measure, let's take a look at the sample images as well to see how the training progressed. So this is the first Prodigy training's epoch, first epoch, second, third, keep going, and eventually we start to get some wear like this, and this is where it ended. When I got to this last image, I was a little hesitant on whether Prodigy actually learned anything. That's why I conducted a second test. So these are the results from the second Prodigy training. I didn't end up using any models from here, but I just wanted to show it because it does kind of converge. Going. And yeah, I think this is the point where it starts to converge. I'm not sure, but it looks like it. I also went back and ran it through the manual XY script to create an XY plot for the first session of Prodigy training. So I'll show this image. Let's zoom in a bit and then right click and drag to pan. So the first epoch, second, third, fourth. And here we can see it's really taking on that style now. Keep going. It's looking nice. Very cool. Yeah. And here you can see on the final epoch, it's overfitted. So there you have it, Prodigy. Very nice. If you recall, the training I showed was an older version of the training settings I was using. After that, I turned on decoupled weight decay and increased the weight decay value from 0.35 to 0.45. So we can go ahead and just take a look at these as well to see what happened. Just for reference, LoRa training takes around 16 hours or so for 30 epochs on 408 images. Once again, back in weights and biases, since we have this very nice chart for comparison for all the losses for Prodigy training, we can compare the higher weight decay training with the previous trainings. The new training is the green one here called Apricot Dream 3. And if you compare it with the previous training, which is Ethereal Cosmos 1, the blue one, you can see that there is a slight gap in between them. So if we open it up, it's minuscule, but you can see a small gap forming in between the training where the weight decay of 0.35 is converging more quickly. This is pretty interesting. We don't have a validation train test split to check our training, so we can't tell what's really going on under the hood. If we hazard a guess, it could be that the weight decay of 0.45 actually is more conservative in adjusting weights as compared to that of 0.35. So let's go ahead and check the sample images to see. Back in XNView MP, so this is the first epoch, second, third. It quickly diverges from what we had before, and it's getting like kind of close, but then it's oscillating very quickly. Eventually it lands on this image, which is the final epoch. We can safely say that this is the one that is overfitting. The question now becomes, what do we use for the final model for Prodigy? I've already run the XY plot in ComfyUI once again, so we can go ahead and take a look. First epoch, second, third. This one's pretty cool, but of course the style's not trained in yet. This one is getting closer to what we want. More. Yeah. So you can slowly see that it's following the same trend as the previous Prodigy training. I actually like both of these here, and this is where I think it starts to converge. So yes, here. This is around epoch 18 out of 30. I think I ended up using 18 out of 30 for this one. Yeah, and I mean, it gets better and worse. Depends what you like. This is pretty nice as well. You can always reduce the strength, but yeah, they're all pretty good, I would say. So there you have it. As we expected, fine-tuning is the best. The equivalent or second best is the LoRa trained with the Prodigy optimizer. After that is D-Adaptation. There are probably more optimal settings, but I didn't explore them further as Prodigy gave me pretty good results. On a side note, there's this competition on CivitAI to train SDXL models, whether they be Finetune or LoRa models. If you guys were interested in training something for it, I hope this video helps you in doing so. By the time this video is out, you should have around 20 days left to submit, so good luck to everyone that wants to try it out. Lastly, our patrons from Patreon. Thanks for your support, and I'll see you guys in the next video. Bye.